Good afternoon, everyone, and welcome. My name is Saad Muhyiddin, and on behalf of the Swedish Knowledge and Research Center and Swedish Dialogue, I'm delighted you could join us for Supercharge Your Research, a practical guide to LLMs for R&D. Over the next 90 minutes, our goal is to give you a solid understanding of how large language models, or LLMs, are revolutionizing the scientific landscape. We'll explore what they are, how to use them effectively, and most importantly, how to do so responsibly. Let's get started. This session is designed to equip you with a comprehensive understanding of large language models, LLMs, and their practical use in research. We'll start by exploring what LLMs are, their significance, and the underlying mechanisms that make them work. You'll learn to recognize key risks, such as misinformation, privacy concerns, and inherent biases that can affect outcomes. We'll also cover how to craft effective prompts to get the best results from AI, and how to critically evaluate the content it generates. Real-world examples will demonstrate how LLMs can assist with literature reviews, coding, and data analysis tasks. Additionally, you'll be introduced to a straightforward framework to help select the most suitable LLM based on factors like privacy, cost, and specific research needs. Finally, we'll discuss strategies for safely and ethically integrating LLMs into your research workflow. Here is our roadmap for the seminar. We'll begin in Part 1 with the fundamentals of what LLMs are. In Part 2, we will cover their critical limitations, which is essential for responsible use. Next, in Part 3, we'll get practical with prompt engineering, the skill of talking to an AI. Part 4 will showcase real-world research applications. We'll then discuss how to choose the right model for your needs in Part 5, and wrap up in Part 6 with a strategy for implementing these tools in your own work. We want this to be a practical session that blends theory with real-world application. Before we dive deep into LLMs, let's take a moment to understand where they fit in the bigger picture of artificial intelligence. This diagram shows the hierarchy. At the highest level, we have AI, which is the very broad field of trying to make machines simulate human intelligence. Within AI, there's a subfield called generative AI, which is what we're focused on today. This type of AI doesn't just analyze data, it creates new content, like text or images. The engine that powers most modern generative AI is deep learning, which uses complex, layered neural networks to learn from huge datasets. And finally, at the very core of our topic, we have LLMs, or large language models. They are a specialized type of deep learning model that has been trained specifically on language tasks. So when we talk about LLMs, we are talking about a very specific but incredibly powerful part of the AI universe. Alright, let's begin with Part 1, LLM Fundamentals. In this section, we'll answer the most basic question: what exactly is a large language model? We'll look at the core idea behind how they work and explore the key breakthrough that made them possible. At its heart, a large language model is a sophisticated prediction engine. It's a program that has been trained on billions of documents. When you give it an input like, "the capital of France is," it doesn't know the answer like a human. Instead, it calculates the most probable next word based on the patterns it learned from all that text. As you can see, Paris has an 85% probability, making it the top choice. This ability to predict the next word, done over and over, is what allows it to generate entire sentences and paragraphs that seem so coherent. So why is this technology a game changer for researchers? The benefits fall into three main areas. First, speed and efficiency. Tasks that used to take weeks, like conducting a literature review, can now be done in a fraction of the time. Second, writing and communication. These tools act as powerful writing assistants, helping you improve grammar, structure, and clarity, which is especially helpful for publishing. Finally, data analysis and discovery. LLMs can analyze huge amounts of text to uncover hidden patterns, generate new hypotheses, and find connections between different fields of study that you might have missed. The entire field of modern AI was transformed by a single research paper in 2017 called "Attention is All You Need." Before this paper, models processed text sequentially, one word at a time, which was slow and made them forget the context in long sentences. This paper introduced the transformer architecture. Its key innovation, called self-attention, allows the model to process all words in a sentence at once and weigh the importance of every word in relation to all the others. This breakthrough solved the problem of long-range dependencies and created the foundation for every modern LLM we use today, from ChatGPT to Gemini. This is a simple way to visualize the transformer architecture that powers modern AI. It has two main parts. The encoder reads and understands the full context of your input text, and the decoder takes that understanding and generates the output, one word at a time. The magic is in the self-attention mechanism, which happens inside these blocks, allowing the model to know which words are most important for understanding the meaning. Since that 2017 breakthrough, progress has been incredibly fast. In 2018, Google's BERT pioneered understanding bidirectional context, which is great for search. OpenAI's GPT series focused on generation, with GPT-3 in 2020 being a major leap. Of course, ChatGPT in late 2022 brought LLMs to the mainstream. From 2023, the race was on for multimodal models like GPT-4 and Google Gemini, which can understand text, images, and more. Now, in 2024 and 2025, we are seeing omni-models like GPT-4o, designed for seamless real-time interaction across text, audio, and video. Before we move on, let's take a moment to discuss what we've covered. I want you to think about these three questions. First, what's one research task you currently do manually that takes forever, and how might an LLM help? Second, before today, how many of you knew that a single 2017 paper created the foundation for every modern AI tool? And third, has anyone here ever gotten a completely wrong answer from an AI and what happened? Let's share some experiences. Now we move to one of the most important topics of the day, the critical limitations of these models. While the potential of LLMs is immense, using them effectively and responsibly means we must understand the risks. In this section, we'll cover the three biggest challenges every researcher needs to be aware of: hallucinations, data privacy, and bias. Think of this as the safety briefing before we use our powerful new tool. The first and most serious risk is what we call hallucinations. This is when an LLM generates information that is factually incorrect or completely made up, but presents it with absolute confidence. A real and dangerous example is an AI inventing fake academic papers, complete with plausible-sounding authors and titles. If you included these fake citations in a literature review, it could destroy the validity of your entire project. The key takeaway is simple but non-negotiable. You can never fully trust the output without checking it against a reliable, original source. So how do we actively fight hallucinations? There are three key lines of defense to protect the integrity of your research. First, the golden rule. Never trust without verification. You must treat every AI-generated claim as unverified until you have personally checked it against a reliable, original source. This is non-negotiable. Second, a powerful technical solution is Retrieval Augmented Generation, or RAG. This system connects the LLM to your own trusted database, like your team's published papers. It forces the AI to find answers in your verified documents before it responds, which dramatically reduces the chance of it inventing information. Finally, you can use rigorous prompting. This means giving the AI clear instructions that limit its ability to guess. For example, explicitly ask it to cite its sources, or to state when it's uncertain. These strategies work together to make your use of AI safer and more reliable. The second critical risk is data privacy. When you upload your unpublished research, data, or ideas to a public AI tool, you risk losing control over it. Your sensitive data could be stored on external servers, accessed by the vendor's employees, or in some cases, even used to train their future models. This can lead to the leakage of valuable intellectual property and may violate data protection laws like GDPR or institutional policies. It is essential to be aware of what happens to your data when you click Submit. To protect your work, you have several strategies. For maximum security, you can use on-premise deployment, where the AI model runs on your own private servers ensuring data never leaves your environment. A simpler but vital step is data anonymization. This means removing all personally identifying or sensitive information from your data before you upload it to any AI service. Finally, for any third-party tool, you must use contractual safeguards. This means having legal agreements in place, like a data processing agreement under GDPR, that define exactly how your data can be handled. Ultimately, the responsibility for protecting your data is yours. The final major limitation we must address is bias. LLMs are trained on the internet, which is filled with historical and societal human biases related to gender, culture, and more. The AI inevitably learns and can even amplify these prejudices. For example, an AI might associate certain jobs with a specific gender, overrepresent Western or English language perspectives in its answers, or even reinforce your own assumptions instead of challenging them. Recognizing that this bias exists is the first step to countering it. Recognizing bias isn't enough. We must actively work to mitigate it. First, use diverse inputs. Instead of relying on one AI, use multiple models and try phrasing your questions from different perspectives to see if the answers change. Second, actively seek what's missing. Don't just accept the first answer. Ask yourself, what perspective is not being represented here? Are there non-Western or non-English sources that are being ignored? Finally, be transparent. When you publish research that used AI, you should disclose which models you used and acknowledge their potential for bias in your limitations section. Bias is not a bug to be fixed, but a feature of the data that we, as researchers, must consciously counteract. Now, let's reflect on these limitations. What specific concerns do you have about AI hallucinations in your own field of research? Have you encountered data privacy issues when using AI tools, and what safeguards do you use? And how do you think AI bias could affect your research outcomes? Let's discuss these critical issues. We've covered what LLMs are and their critical limitations. Now let's move into the how-to. Part 3 is all about practical prompt engineering. This is the skill of writing effective instructions for an AI to get the results you actually need. We'll start with the basic techniques, and then build up to more advanced patterns specifically designed for research contexts. Before we get into different techniques, let's start with the absolute basic. What is a prompt? Simply put, a prompt is any instruction you give to an AI. It can be a question, a command, or even just a few words to start a conversation. The most important thing to remember is that the quality of your prompt directly controls the quality of the AI's answer. Think of it like giving a task to an expert assistant. The clearer and more detailed your instructions, the better the result will be. A good prompt often tells the AI what to do, gives it the necessary background context and data, and specifies the format you want the output in. The most straightforward way to interact with an AI is zero-shot prompting, where you simply ask it to perform a task without giving any examples. For instance, summarize this article. The main pro is that it's fast and requires no preparation. However, there are cons. Its success depends entirely on the model's pre-existing knowledge. There is a higher potential for errors because there's no specific guidance, and you have limited ability to customize the output format. It works best for simple, well-defined tasks. This method is fast and requires no preparation, which is great for straightforward tasks where the context is obvious. However, its success depends entirely on the model's pre-existing knowledge, so the quality of the output can vary. When you need more control over the output, you can use few-shot learning. Here, you guide the AI by providing a few examples of the desired output before you give it the actual task. As you can see in the example, we first show the Model 3 citations formatted correctly in APA style. Then, we ask it to format new references in the exact same way. This technique is incredibly effective for tasks that require a specific format or have clear rules, as it dramatically improves the consistency and accuracy of the results. For more complex problems, a powerful technique is chain-of-thought prompting. Instead of just asking for a final answer, you instruct the AI to think step by step. For example, rather than just asking for an evaluation of a research proposal, you guide it through a logical sequence. First, assess the research question, then the methodology, then feasibility, and finally provide an overall evaluation. This is best for complex analysis or problem solving, because it forces the AI to break down the problem, which improves accuracy and transparency, allowing you to see its reasoning. We can make our prompts even more effective by using specific patterns tailored for research. This chart shows how adding layers to a prompt improves its effectiveness. For example, adding clarity is key. Instead of a vague request like "help with my paper," you should be specific. Suggest 3 recent studies for my neuroscience paper. Using role prompting is also powerful. Tell the AI to act as a senior biostatistician to activate its domain-specific knowledge. Finally, providing context about your work helps it give tailored advice. Let's talk about preventing errors. A simple but crucial technique is using delimiters. Delimiters are clear boundaries, like triple quotes, brackets, or XML tags, that you use to separate your instructions from the data you want the AI to analyze. In this example, we tell the AI to analyze the text between the triple quotes. This simple trick prevents the AI from getting confused and mixing up your instructions with your content. It's a fundamental best practice for getting accurate and focused results. Iterative refinement. Improve results through step-by-step feedback loops. Begin with a basic prompt. Review the AI's initial answer, then clarify, add details, or adjust your question based on the output. Repeat this cycle until the output meets your needs. It's also useful to know that there are 2 levels of prompts that control an AI's behavior. First, there's the system prompt. Think of this as the AI's constitution or permanent job description. It's usually set by the developer in the background and tells the AI what its persona and rules are. For example, you are a helpful research assistant who always cites sources. Then you have the user prompt. This is the question or command that you, the user, type into the chat box in each turn of the conversation, like, "Summarize this article." The AI then follows your specific user prompt while adhering to the broader rules set by its system prompt. Understanding this distinction helps explain why different AI tools can have such distinct personalities and capabilities. So how do these 2 types of prompts work together? Think of it like a funnel. The system prompt acts as the funnel itself. It sets the broad rules and defines the AI's persona. For instance, it shapes the AI to be a, quote, helpful research assistant. Then, your user prompt, your specific question like "summarize this article," is what you pour into the funnel. The AI processes your request, but it's constrained and shaped by the rules of that funnel. What comes out at the bottom is a shaped output, an answer that directly addresses your question, but is delivered in the formal, objective tone of a research assistant, as defined by the system prompt. This combination is what allows developers to create specialized AI tools that are fine-tuned for specific tasks like legal analysis, creative writing, or, in our case, research. Finally, it's important to understand that as AI models have evolved, the skill of interacting with them is also evolving. We are moving away from simple prompt engineering to a more advanced concept called context engineering. In the past, with smaller models, success was all about crafting the perfect, clever question. But today's models have massive memories. They can read entire research libraries in seconds. This changes the game. The key skill now is not just asking the right question, but providing the right background information. This is context engineering. It involves designing the AI's entire knowledge environment for the task. This means using techniques like retrieval augmented generation, RAG, to give it a specific set of documents, setting a detailed system prompt to define its role, and using the huge context windows of models like Gemini or Llama 4. Essentially, we're shifting from just talking to the AI to shaping the world the AI thinks within. This leads to far more accurate and reliable results. The system prompt acts as the funnel itself. It sets the broad rules and defines the AI's persona. For instance, it shapes the AI to be a, quote, helpful research assistant. Then, your user prompt, your specific question like "summarize this article," is what you pour into the funnel. The AI processes your request, but it's constrained and shaped by the rules of that funnel. What comes out at the bottom is a shaped output, an answer that directly addresses your question, but is delivered in the formal, objective tone of a research assistant, as defined by the system prompt. This combination is what allows developers to create specialized AI tools that are fine-tuned for specific tasks, like legal analysis, creative writing, or, in our case, research. That brings us to the end of Part 3. We have some time for questions and reflections on these prompting techniques. Which of these have you tried? What barriers do you see to using them in your work? Also, for those who want to dive deeper, I have created a series of short tutorial videos on prompt engineering that break down these concepts even further. You can find the link on my blog. This funnel diagram shows a simple but robust framework for ensuring the quality of AI-generated content. You start with the raw output from the AI at the top. The first step is to verify the content, meaning you double-check all facts and citations against reliable sources. Next, you refine your prompts by iterating on your questions to improve the output. Finally, you validate the key findings to ensure they are supported by real data, not just AI assertions. By passing the AI's content through these 3 filters, you produce high-quality, trustworthy results for your research. Now that we know how to interact with LLMs, let's look at where they are making a real impact. In Part 4, we will explore specific R&D applications. We'll examine how these tools are being used for literature reviews, code generation, and data extraction, looking at both the powerful advantages and the critical limitations of each. One of the most impactful applications is automating literature reviews. The advantages are transformative. Studies show LLMs can reduce the manual screening workload by anywhere from 33% to over 90%. When criteria are well defined, they can achieve high accuracy. However, the limitations are equally critical. The quality depends entirely on how clearly you define your criteria. There's a major risk to reproducibility if a proprietary model updates, and these models can amplify existing biases by favoring highly cited papers. They assist, but cannot replace, human expertise for complex judgments. Here's a real-world case study. A healthcare company used an LLM platform to automate their systematic literature reviews, cutting the review time from 12 days down to just 2 hours, a time saving of over 90%. This allowed their human experts to stop doing tedious manual screening and focus on the higher-level work of synthesis and interpretation. The key insight from this and other studies is that success hinges on the quality of your inputs. LLMs amplify your methodology at scale. If you provide clear, robust research protocols, you will get reliable and rapid results. If your inputs are poor, the AI will simply produce low-quality results even faster. Another major application is code generation. The benefits here are huge. LLMs can dramatically speed up the creation of prototypes and data analysis pipelines. They lower the technical barrier for researchers who aren't expert programmers, and can even help make novel discoveries by generating new equations. However, the risks are severe. The code an AI generates can have hidden bugs or silent errors that are hard to find. Over-reliance on these tools without validating the code can lead to flawed results and the loss of essential programming skills for the researcher. In a recent study, researchers used GPT-4o to power an autonomous simulation agent for a polymer physics problem. The AI achieved what was called near-flawless execution, managing the entire research project from planning and coding to data analysis and creating publication-level figures. While it still ran into some issues like debugging loops, it demonstrated the incredible potential of these tools. The key insight here is that the researcher's role is evolving. You may no longer be a line-by-line coder, but rather a high-level architect and critical evaluator. You must understand the logic of the code, even if you didn't write every line yourself. LLMs are also incredibly powerful for extracting structured data from messy documents. This is being used right now in clinical trials to automatically match patients to studies by parsing complex eligibility criteria, in finance to pull specific data from PDF invoices, and even in historical research to process archived documents with mixed handwriting and stamps. However, this application comes with significant reliability challenges. You often have to deal with data format chaos, where real-world documents are messy and unstructured. When using public tools, you have a lack of model control, as they can update without notice. Finally, the high cost of pay-per-use APIs can become a major issue for large-scale projects. This brings us to two fundamentally different ways to use these tools. On the left, we have the public cloud API. This is where you use a ready-made service from a company like OpenAI or Google. You send your data to their servers, and they send back a result. The key thing to understand about its cost is that it has a low upfront investment but can become very expensive at high volumes. On the right is the in-house solution. This is where you run an AI model, often an open-source one like Llama, on your own private servers. Your data never leaves your secure environment. This requires a high upfront investment in hardware and talent, but your long-term operational costs are much lower and more predictable. This leads to a classic strategic choice. Should you build or buy? Let's look at the case study of Glean.ai. They shifted from external APIs to an in-house solution and, as a result, boosted their data extraction accuracy from 70% to over 90%, while cutting costs by 30%. Their story perfectly illustrates the decision framework. You buy access to an external API when you need to prototype quickly or for standard tasks. You build a custom in-house solution when you are working with high-volume, unique data, where you need maximum control, security, and accuracy to create a long-term competitive advantage. To recap Part 4, we looked at 3 key R&D applications. For literature review, we saw a massive reduction in manual work, but noted that accuracy depends on clear criteria. For code generation, we saw faster prototyping, but highlighted the risk of hidden bugs. And for data extraction, we discussed the trade-offs between accuracy, privacy, and cost. Now let's take a moment to discuss. What direct experience do you have with these tools? What obstacles do you see to implementing them in your own work? And what's one concrete action you could take to start testing these methods? Choosing the right model is crucial for research success. We'll navigate the landscape strategically. We will talk about using context capacity, modality support, privacy governance, and budget management considerations. Understanding model capabilities and mapping them to research budgets and institutional constraints. Matching optimal models to specific research workflows, whether for literature review, document analysis, coding support, or hypothesis generation. This timeline really captures the incredible acceleration we've seen in AI development since the Transformer paper. It started in 2018 with Google's BERT, which was a breakthrough in understanding bidirectional context, the meaning of words based on what comes before and after them. In 2019, OpenAI's GPT-2 showed the world that I could generate impressively coherent text. But the major leap came in 2020 with GPT-3, a massive model with 175 billion parameters that unlocked few-shot learning, the ability to perform new tasks, just from a few examples. Of course, November 2022 was the inflection point when ChatGPT brought this power to the mainstream. This ignited an industry-wide race, and just a year later, in December 2023, Google launched Gemini to compete directly with GPT-4 in multimodal processing, understanding more than just text. In May 2024, GPT-4o introduced real-time, fluid voice conversations, making interaction more natural. And now, in June 2025, we have models like Gemini 2.5, which are pushing the boundaries of reasoning with new thinking models. First, let's look at OpenAI's ChatGPT, including the GPT-4o model. Its core strength is its market-leading general intelligence and natural, creative conversation. It's also highly versatile, with strong multimodal capabilities for text, voice, and image. Its main weakness is that it's still prone to factual hallucinations in certain domains, and its API costs can be a concern for large-scale enterprise use. It is best fit for R&D functions like rapid prototyping, literature and patent review, brainstorming and content creation. Next is Google's Gemini, including the 2.5 Pro and Ultra models. Gemini's core strengths are its leading factual accuracy and its deep integration with the Google ecosystem. It boasts a huge context window, making it excellent for analyzing large documents, and offers strong enterprise security. Its weaknesses are that it's still evolving in highly technical code generation compared to the best coding models, and advanced features may require using the Google Cloud Platform. It is best fit for real-time fact-checking, large-scale document analysis, and R&D workflow automation. Here we have Anthropic's Claude 4. Its key strength is its state-of-the-art safety and ethical alignment, which they call constitutional AI. It has a large 200,000 token context window and is excellent at handling long-form text and providing transparent, step-by-step reasoning. Its typical weaknesses are that it can be slower for very complex queries, and it has fewer third-party integrations than its main competitors. It is best fit for reviewing sensitive or confidential data, multi-step analysis, and technical writing in regulated sectors. Now for xAI's Grok 4. Its core strength is its top performance in academic, STEM, and reasoning benchmarks. It has a large context window, is multimodal, and features a heavy multi-agent mode for deep dives into problems. However, it is slower and more computationally expensive than simpler models, and its user interface is still best for technical power users. Grok is best fit for advanced technical and scientific R&D, complex reasoning, algorithm development, and business simulations. Finally, let's look at DeepSeek R1. As an open-weight and accessible model, its main strength is that it's highly cost-efficient and excels at math, logic, and technical reasoning. It provides transparent step-by-step output, which is great for technical work. Its weaknesses are that it has a smaller ecosystem than Gemini or ChatGPT and requires more manual fact-checking in niche fields. It is best fit for academic and industrial research, programmatic data analysis, and open science projects that require transparency and flexibility. Now let's look at a leading open-source model, Meta's Llama 4 Scout. Its absolute standout strength is its massive 10 million token context window, which is the largest available and makes it the undisputed leader for long document analysis. It's also highly cost-efficient and offers the transparency of being open source. Its weaknesses are that its reasoning and coding skills, while strong, may not match the absolute top-tier proprietary models, and enterprise support is less direct. Llama 4 Scout is best fit for comprehensive literature reviews, analyzing entire code bases, or any research that involves extremely long documents, where cost is also a key consideration. To make a strategic choice, you need a framework. This diagram shows the 4 pillars of model selection. Pillar 1 is context length, how much information the model can handle, which is vital for long documents. Pillar 2 is modality support. Can it process text, code, images, and other multimedia? Pillar 3 is privacy and security, a critical factor for sensitive data, determining if you need a private deployment compliant with GDPR or HIPAA. And Pillar 4 is budget and economics. What are the API fees and maintenance costs? Evaluating every potential model against these 4 pillars will lead you to the right choice. To make this more practical, here's a quick selection guide based on common research tasks. If you are working on complex theoretical problems or hypothesis generation, you'd look at top performers like Google Gemini 2.5 Pro or Claude 4. If your main task is a comprehensive literature review with thousands of articles, you need a model with a massive context window, like Llama 4 Scout. For generating scientific code or running simulations, models like Claude 4 and DeepSeek R1 are excellent choices. And for interpreting mixed data, like a chart in a research paper, you would turn to multimodal leaders like GPT-4o and Gemini. So what are the key takeaways from model selection? First, take a portfolio approach. Use different tools for different tasks. Second, understand the trade-offs between open-source models that offer control and proprietary models that offer peak performance. Third, be mindful of cost, as advanced reasoning can be expensive. And most importantly, never compromise on research integrity. Your standards for accuracy and ethics always come first. With that, let's open it up for discussion. What specific research challenges are you facing where one of these models could help? For our final section, we'll address the crucial question of implementation. We know what LLMs are, we understand their risks, and we have a framework for choosing one. Now, how do we bring them into our organizations in a structured way? That is the focus of Part 6, Implementation Strategy. We'll outline a systematic framework for integrating these powerful tools thoughtfully and sustainably. Systematic framework for LLM deployment. This structured approach transforms LLM integration into a methodical, research-grade methodology. Step 1. Define use cases. Map specific research tasks to LLM capabilities with precision. Set clear success metrics and outcomes for each application, e.g., automating literature coding, generating hypotheses, analyzing qualitative data. Step 2. Audit data. Assess data sensitivity, volume, and format requirements upfront. Establish privacy boundaries and compliance needs before any data interacts with an LLM. This is crucial for research integrity and publication without compliance issues. Step 3. Score models. Systematically benchmark candidate models on representative research tasks using your own data. Evaluate accuracy, speed, cost, and trade-offs. Step 4. Deploy and monitor. Implement with continuous performance tracking. Establish feedback loops for ongoing optimization, as model performance can drift and research needs evolve. Systematic framework for LLM ongoing elements include pilot program strategy. Start with low-risk, high-impact use cases. Run controlled experiments with clear success criteria before scaling. Performance baselines. Establish human performance benchmarks and track quantitative/qualitative outcomes to validate LLM integration over time. Iterative refinement. Build regular reassessment and adaptation into workflows as the LLM landscape moves fast. Risk mitigation. Maintain human oversight protocols for critical decisions, audit trails, and validation procedures to ensure research integrity. Ethical compliance is a non-negotiable part of any AI implementation, and it rests on these 3 core pillars. First is data privacy and ethics. This means adhering to laws like GDPR, following your institution's protocols for classifying and securing data, and having clear policies for user consent and data deletion. Second is regulatory compliance. This involves getting IRB approval for human subjects research, following the AI use policies set by federal funding agencies, and complying with any industry-specific regulations, like those in healthcare or finance. Finally, and most importantly for us as researchers, is maintaining research integrity. This requires being transparent about your use of AI in publications, documenting your methods so they can be reproduced by others, and having active protocols in place to detect and mitigate the biases we discussed earlier. To help you put this all into practice, here is a practical toolkit. First, use structured evaluation frameworks to benchmark model performance on your specific use cases. Second, create risk mitigation checklists to proactively identify potential issues like data leakage or bias. Third, develop an institutional playbook to document best practices and create standard operating procedures for your team. Fourth, use template documentation for your prompts and validation logs to ensure your work is consistent and reproducible. Finally, invest in knowledge sharing through workshops and internal training to upskill your entire team. The key takeaway for this final section is that successful LLM implementation is a journey that requires systematic planning, strong ethical consideration, and a commitment to continuous optimization. The goal is always to build sustainable practices that enhance, not replace, human expertise and judgment. Let's use this to frame our final reflection. Thinking about your own work, what is one specific use case you could start with? What barriers do you face? And what resources would you need to move forward? Remember, focus on one application at a time for practical, meaningful progress. So where do you go from here? We encourage you to start small with a pilot project, using the evaluation framework we discussed today. Establish clear metrics to measure your success. Work to build institutional policies for responsible AI use. And most importantly, share what you learn with your colleagues to advance collective knowledge. To help you on your journey, this slide lists several foundational resources, from the original academic papers to practical prompt engineering guides and ethical guidelines from respected institutions. Thank you for exploring this evolving landscape with us. And finally, a little about my background. I have spent my career at the intersection of engineering, education, and technology. This journey has fueled my passion for making complex topics accessible and for exploring the ethical dimensions of new technologies, which ultimately led me to write the books you see here on computer ethics and prompt engineering. Thank you once again for your time and attention. I am happy to take any final questions.